Hello and welcome to Chapter 5, which discusses Ethernet. The previous chapter we looked at the bottom two layers of the OSI model, the physical layer and the data link layer. We spoke about different protocols including Ethernet. We discussed token ring briefly. We spoke about FDDI, the Wi-Fi protocol. This chapter, though, is devoted to the Ethernet. So we zoom in, we take a closer look at Ethernet because it's the most widely used LAN technology. Wherever you look, a LAN is going to be implementing Ethernet, and that's why we would like to get into more details about this protocol. We will begin with a summary of what we learned from the previous chapter that applies to Ethernet, and then we move on to more details. So if we remember, in the last chapter we said the data link layer is divided into two sublayers, the MAC and the LLC. IEEE protocol 822.3 spans and covers the physical layer and the MAC sublayer, while the IEEE 822.2 covers the LLC sublayer. The role of the LLC, we said, covers basically interfacing between upper layers from the network and up, and the basically the medium. Okay, now if you look at these layers from the network and above, we said these are implemented in software. So in the operating system, whenever you install Windows, it comes with the implementation of things like TCP, IP, and so on. Okay, so these are again implemented in software. If you look at the bottom from the MAC layer and below, if you're wondering how these are implemented, and the answer is these are inside your network card and of course the actual medium, which is the twisted pair cable. Okay, so what the LLC, the role that the LLC plays is interfacing between the software in the operating system and your actual hardware, which is the NIC card and the cable. Okay, the question is, how is the LLC implemented? And the answer to that is it's as a device driver. If you remember back in chapter 2, we said there are multiple components in an operating system. One of these is the device drivers. To give you a simple example, let's say I wrote a Java program and I wrote a statement like system.out.print and so on, and then I said hi. Okay, when you run such a Java program, the result, this word hi, is displayed on the screen. Now your operating system, the way it understands things is basically this is just a write operation. It needs to write something, and that thing is being written in this case to your video card, which is going to be mirrored to the screen. It doesn't know the language of the video card. It doesn't speak that language. All it knows is I need to do a write operation. The question becomes who's going to do the translation, and the answer is the device driver. So they're all at place. So whenever you buy new hardware, you install device driver. Why? Because it basically speaks the language of the operating system and it understands its own language, so it can do the translation between the two. Let's say we take the same program and we decide to redirect the output, place it in a file, okay, called out. Okay, what happens in this case, again, it's the same program and there is a write operation. Your operating system, all it knows is I need to write. Then since this is being written to the file system, again you have some way of translation. So back to our context, we're talking about the LLC. The LLC is basically you're talking about another piece of hardware here, which is your NIC card and your actual cable. And the one that talks to these, you have a piece of software in between, which is the LLC, the Logical Link Control sublayer. The MAC itself is again implemented as hardware. Okay, so protocols like Ethernet span the bottom two layers. There are different variants of Ethernet that we will look at in today's lecture. Okay, so briefly, just so that we recap the things we learned about Ethernet from the previous chapter, it does two main functionalities. The first one is data encapsulation at the sender, and obviously decapsulation at the receiver. And the second thing is media access control, which is where it gets its name from. Okay, when data encapsulation happens, that basically includes achieving multiple goals. The first one is frame delimiting, meaning where does a frame begin, where does it end. Without that, there is no structure. You just have a sequence of zeros and ones that goes on and on and on, which there is no way to interpret. Frame delimiting defines the boundaries, where a frame starts, where it ends, so that it can be processed accordingly. The second thing it does is addressing, identifying who needs to be receiving this, who sent it, and so on. And the third thing, which appears in the trailer, is adding a CRC for error detection. The second functionality is basically regulating access to the media. So basically, who gets to talk and who has to wait, and then how to recover when problems do occur if multiple communications occur at the same time. Okay. So as you can see here, this illustration is a zoomed in picture. Here's our LLC, here's our media access control, and that's going to be dependent on the type of medium that we have and the signaling approach used. So is it coaxial that we're using? Is it fiber optic? Is it unshielded twisted pair? And the different characteristics of these. Again, I'll come back to this later on. Okay, if you remember, we said Ethernet falls into the category of contention-based medium access control, and what that means is basically any device that has something to send, it can do so. It doesn't have to basically take turns. So one benefit of contention-based medium access control is that they do not have the overhead of controlled access, having to wait your turn by possessing the token. The problem with this approach is, of course, it doesn't scale very well, meaning as the number of nodes increases, or as the amount of traffic increases, the probability of successful access decreases, and the chance of collision will go higher and higher. Also, recovery from such collisions is going to introduce its own overhead, which means eventually the achievable throughput is going to be minimal. Okay, the mechanism that's used for regulating the media access and recovering from collision, if you remember, Ethernet uses the CSMA-CD, the Carrier Sense Multiple Access with Collision Detection, and I'm not going to discuss that again because we already went over it. But the one thing I have to, that's extremely important to understand, is that CSMA-CD is used by traditional forms of Ethernet. Meaning, nowadays, if you look at how networks are designed, basically things look like this. You have a switch. The switch has multiple ports on it. It depends on the model of the switch. You might have 12 ports, 24 ports, and so on. And then a computer is plugged into each one of these ports. Now, forgive my drawing skills with the mouse. It's not going to be great. And in general, it's not great. But anyway, you get the idea. So here's computer A, computer B, and so on, computer N, as many computers as we have. The one thing that I want you to get out of this is the following. Let me change colors. So what happens is when A communicates with this port on the switch, so here is our switch, okay? Any communication between A and the switch happens over one dedicated channel. What that means is basically if node N here happens to also be transmitting at the same time, a collision will not occur. Why? Because again, there is a dedicated channel between these two, between A and this port, and between node N and this port. So this is a great plus, and this is part of the reason why Ethernet speed improved over time, is because you no longer have to deal with the issue of a shared bus. Moreover, let's say at the same time the switch is trying to forward something to node A while node A is sending something to the switch. This also can occur with no collision. Why? Because each one of these dedicated channels is full duplex. So the communication can occur in both directions at the same time. The big implication of all this talk is that basically there are zero collisions in today's Ethernet, which means it no longer has to worry about the CSMA-CD. CSMA-CD isn't used in modern Ethernet networks. Now, I don't want you to think, okay, there is no sharing whatsoever, because initially, as the switch is learning where things are located, let's say first time it received the packet that's destined to A, and it doesn't know where is that A, where is that address. It forwards the packet out all the ports. So still there is that, while the switch is still learning, it's acting as a shared bus. Okay, but once it learns where everything is located, then there is no sharing. Basically, things move only between the communicating nodes. All right. So again, the underlying topology with Ethernet logically is basically a multi-access bus. There are implications to that. First of all, we're talking about shared medium, and second of all, what that means is every node will be receiving everything. Again, the same thing applies with the switch initially, while the switch is still learning where things are located. What that means is basically, how is, let's say, node A here is trying to talk to node F here. Since everyone is going to be receiving the frame that's coming from A, how does it tell others that, hey, this is intended for node F? Now, one way it can do this, if you remember, we had the protocol stack, right? And let's say this is happening, let's say it's web access, so you have a web document, which means you have HTTP here, and then you have TCP below, and then you have IP below that, and then you have the network access. So here's your access layer. Okay, so and we mentioned that this translates to, you have some data, payload, this is your web page content, right? To this, TCP or HTTP first is going to add its own header, and then TCP adds its own header and passes it down, and then IP adds its own header and passes it down. But before we talk about adding the DLL header, if we zoom in on that IP header, what's inside it, among many other things, is the source IP address and the destination IP address. Okay, so you might be thinking we can solve our problem by, when node A specifies node F, all the nodes need to do is just peek inside the IP header to tell who the destination is. This is possible in theory. The problem with it is it's going to introduce a large amount of overhead to process each IP packet, to decapsulate each IP packet to look inside it. And this is going to be even exaggerated further when you have large amounts of traffic. So as a solution, that's not how the network access handles the problem. What it does is, in the header, it adds its own source address and destination address. But these, if you recall, these are different types of addresses. They're not IP addresses. These are MAC addresses. And if you remember, and I'll come back to this later today, these are meant for end-to-end communication. So they specify the original source of a packet and the ultimate destination, while the addresses here will be used for intermediate steps to keep moving from point A to intermediate points until it makes it to the destination. So anyway, let's focus now on the Ethernet identity, meaning identifying nodes through their MAC addresses. If you recall, we said a MAC address is 48 bits long. Each 8 bits is 1 byte. So if I take 48, I divide that by 8, and I will be getting 6 bytes, right? So a MAC address is 6 bytes long, and each byte is represented as 2 hexadecimal digits, which means the same address can be represented as 12 hex digits. Okay, so that's a MAC address. Now, one thing that's extremely important for us to realize is that MAC addresses are globally unique. Just like your car's VIN number, no two cars produced have the same VIN number. The way that's controlled to make sure uniqueness is basically you have some standards organization to do it. In the case of Ethernet, the IEEE has certain rules enforced so that any vendor that produces and sells Ethernet devices, they must first register with IEEE. When they do register, the IEEE assigns them what's called organizationally unique identifier, and that identifier is 24 bits long. Okay, so you go to a vendor like Cisco, and they're assigned by the IEEE the hexadecimal digits 00602F, which is basically 24 bits. And then what the IEEE asks for of each of these vendors is for the remaining 24 bits of a MAC address is to choose a unique number. So basically a company like Cisco will begin with this, and then for the remaining ones it will begin with maybe all zeros for the 24 bits, then zeros ending with a 1, then a 2, and so on. So as long as this is unique, uniquely assigned from the IEEE to each vendor, and each vendor makes sure that the remaining bits are also unique, then every MAC address is going to be unique. Okay, now these MAC addresses come, they're called burnt-in addresses, and you can see them printed on a card, and regardless whether it's a card or just an integrated card within a motherboard, it's the exact same idea. But basically the reason it's called burnt-in address is because historically this used to be written into read-only memory. Since it's read-only, it cannot be changed. Nowadays though, things changed. With modern operating systems and NIC cards, you can actually in software go and change the MAC address of a device. The implication of that, in the old days people used to rely on filtering, like controlling which traffic is allowed in and which traffic isn't based on the MAC addresses, because that used to be secure, because no one can forge MAC addresses. This is no longer secure nowadays because again people can change it in software. Okay, so let's look at this video. So 5115. Alright, so here we have node H1 trying to talk to H3. Inside the frame, notice it includes, here's the data including the IP header and the IP addresses and everything, but notice that it attaches its own header which includes the source address, meaning the MAC address of this H1, and the destination address, which is the MAC address of the destination H3 in this case. Notice also that when this frame is forwarded, it's shared media, everyone gets it, but everyone looks at the everyone looks at the destination address to determine whether it's the intended receiver or not. Anyone who isn't will drop the frame, except the one that's meant to receive it. So that's part of the reason why we have these MAC addresses to identify senders and receivers. Okay, so let's look at one of the great things about Ethernet, and the reason it became the universal de facto protocol used in LANs, is due to its ability to improve over time. So let's look at its history, which is beneficial in its own right, but we will need it also in our further discussion. So 5121. Okay, so where did Ethernet start? If you recall, this was back in 1973 at Xerox Corporation, and it was called Ethernet. Okay. Later, Xerox collaborated with two more companies, Intel and Digital Equipment Corporation. The three of them created an industry standard called DIC standard. The acronym comes from the initials of the three companies, and this ran at 10 megabit per second over coaxial cables. Later, 3 years later, the IEEE took this and made it into a standard. which was called the 10 base 5. In case you're curious, the 10 in this name is for the speed, 10 megabit per second. The base is for baseband communication, for the signaling approach basically, as opposed to broadband. And the 5 is for the limitation on the distance. It can be up to 500 meters, meaning nodes cannot be farther apart than 500 meters. Anyway, moving on. So again, this ran over what's called thick coaxial cables, which basically cables that have certain characteristics in terms of resistance and so on. Later, 2 years later, they came up with the 10 base 2. So this one runs over thin coaxial, which has basically different characteristics from thick coaxial. It's easier to work with, cheaper, and so on. In this case, as you can see, it's a base 2, meaning the distance can be up to 200 meters. Moving on, in 1990, 5 years later, they came up with the base T, and from that moment on, all the Ethernet you see no longer uses coaxial. It's based on twisted pair technology. Okay, so as you can see, the T here is for the type of technology. In case you're curious about the distance, how far nodes can be, they can be up to 185 meters apart. So all the way up to 1990, as you can see, the speed was, or up to 93, the speed was stuck at 10 megabit per second. So this one is over fiber optic, different medium. All the way until in 1995 they came up with the 100 base type of Ethernet. So this was called fast Ethernet to compare it with the old one, and there are various standards. Some of them run over fiber optic, some of them run over twisted pair. In 98, 3 years later, this has gotten better, and they introduced the gigabit over fiber optic and later over twisted pair. And then in 2002, the 10 gigabit over fiber and then later over twisted pair. And nowadays it can be up to 40 or even more gigabit per second. So this progression of Ethernet is again important to for us to know as networking people. Now you might be wondering, in terms of the frame structure, all of these different ones that we mentioned almost have the same frame format. Okay, if you're wondering why then the difference in speed, the reason is basically using different physical layer in terms of, if you remember, modulation, encoding schemes, the use of switching instead of shared medium. So all these contributed to being able to speed up Ethernet. Okay, so we said the frame more or less is the same for the different standards, but there's a couple of differences that are extremely important to highlight. The first one between the IEEE version and the Ethernet 2, which is the DICS version, the 3 companies standard. There's an important difference to understand because, by the way, TCP/IP networks follow this frame format. So let's see where the difference lies. The first thing is, notice that there's this 2-byte field here that's called length, which basically tells how large the frame is. Now this goes from the destination address all the way to the frame check sequence, meaning the frame length doesn't include the preamble and the start of frame delimiter. It just identifies how long this is. Now notice that Ethernet imposes a limitation on the size of a frame. A frame cannot be shorter than 46 plus, of course, this information here in the header and the trailer, and up to, it can be no larger than 1500 bytes, meaning once you add these 6, 12, 14, 18, basically you're talking about the limitation being up to 1518 bytes, and this one basically is 64, meaning a frame can be no smaller than 64 bytes and no larger than 1518 bytes. So that's in terms of frame limitation, and this limitation also applies to Ethernet 2. The second difference is basically Ethernet 2 uses an 8-byte preamble, okay, while 802.3 uses a 7-byte preamble and 1 byte to indicate the beginning of a frame. Now, in case you're wondering what the hell do these do, basically the preamble is meant for synchronization. If you remember before in the physical layer, we spoke about different methods of communication, synchronous versus asynchronous. So to synchronize the sender and the receiver, they begin with a certain bit sequence to get their clocks synchronized. And then this one is meant just to give the destination alert that, hey, communication is about to begin. So again, two differences between the two. So here we have length. What do we have in the Ethernet 2? Instead, what the DICS or Ethernet 2 standard has is a type subfield. If you remember, in the logical link control sublayer, we said it identifies what data is being carried in the payload. It could be IPv4, it could be IPv6, it could be ICMP. So the purpose of this field, instead of being the length, with Ethernet 2, it's meant to specify a code that reflects what protocol data is being carried. Okay? If this is too vague, basically there is something called ether type protocol list. If you Google this and press enter, the very first link that comes up is IEEE 822 numbers, and if you scroll down, it shows you the Ethernet values for different protocols. If I search for IPv4, for example, notice that the code for it is in hexadecimal. Notice here it says ether type in hex. It's 0800. Okay, so different protocols that are being carried in an Ethernet frame will have in that type field a specific value based on this standard that identifies different numbers. Okay, so again, with 822.3, this field specifies the length. With Ethernet 2, it specifies the type as a number reflecting what is being carried. One question that may come to your mind, okay, here we know what the length of the frame is, but how would a node know how big the frame is in this case? The answer is very simple. It keeps listening to the channel, and once it ceases hearing any signal, it means, okay, communication ended and the frame ended. Okay. Alright, so what would happen if a frame happens to be less than the minimum allowed, less than the 64 bytes? Such a frame is called a runt frame. Just so that you don't think this is useless talk, if you go inside Packet Tracer and you issue the command show interfaces and you choose one port like fast Ethernet 01. Notice first of all that I'm in privilege mode when I issue this command, but basically I'm asking for information about the first port on my switch. One of the things you see here toward the bottom, notice here where it says 0 runts, meaning so far in the communication, 0 frames happen to be smaller than what's allowed. It also says 0 giants, meaning 0 frames so far that are larger than the maximum allowed, and so on. Alright, one important question. Let's say a computer receives a frame. How does it determine, hey, do I interpret it according to this way or according to this way? The answer is very, very simple. If you remember, we said that a frame can be up to 1500 bytes, right? And you add to this the 18 bytes, so which means the maximum value, if it happens to be a length field, is going to be 1518 bytes, right? Well, the way the types are chosen by that IEEE 822 standard, types are chosen to be always values greater than that. So, if you see a value that's 0x, meaning hexadecimal 600 and above, which is basically 1536 and above, then the value must reflect an ether type protocol. If the value is 1500 or below, then it means this is an IEEE and it's reflecting the frame length. So again, you go by the value. If the value is above a certain limit, then obviously it's not a length because the length can't be above 1536. So very clever design. Okay, so let's talk now about MAC addresses. We said these are represented in hexadecimal, so it's important for us to remember the hexadecimal numbering system, especially in the next chapter we'll also see that it's used to represent IPv6 addresses. We as humans prefer decimal because that's what we use all the time. Computers understand binary, basically voltages on and off. But then what is the point of this hexadecimal? Well, the idea is basically, if you look at a number like 15, representing this in binary takes 4 digits, so it gets longer and longer. The point of hexadecimal is a way of abbreviating binary numbers. Usually when we deal with chunks of size 1 byte, a byte is 8 bits. If you take an 8-bit 1 byte number like this one, if you represent it in hexadecimal, it would be only 2 digits. So this is very convenient, and that's why people use hexadecimal instead of binary, again as a method of abbreviation. Now recall that the hexadecimal number system is base 16, so you have 0 to 9, the digits that we're familiar with, and for the remaining base digits in it, it borrows letters. And that's why we say any hexadecimal digit is the equivalent of 4 bits. Why? Because 15, which is 1 digit in hexadecimal, is a representation of 4 bits in binary. One thing that's important, if you need to do conversions, you can go directly from decimal to hex or hex to decimal by doing, powers of 16 instead of powers of 2 and division. However, it's much easier if you need to do so to go first to binary. So from decimal go to binary, and the conversion from binary to hex is very straightforward. Likewise, if you would like to go the other way, first convert to binary before you go to decimal. It will be much easier, and you can, with some practice, become very fast at it. Now, if you look back, when we looked at the limit of what the values, notice we said 0x0600 is a hexadecimal value. That's usually how we express hexadecimal numbers, by indicating before them the prefix 0x to indicate that, hey, this value isn't a regular decimal 600, no, it's a hexadecimal 600. So even in programming, like here is a little Java program where we're trying to print the value 0x55. Notice when I ran this code, it shows me that the value is 85. Java understood that I meant 55 isn't decimal, it's a hexadecimal value, and that's why I did the conversion. This 55 that you see here is from the string itself. Okay? Anyway, so that's how usually we represent it. Okay, so when you look at different platforms, you will see MAC addresses presented to you in slightly different formats. On Windows machines, you will see them as 2 hex digits followed by a dash and so on. On Macs and Unixes, they are separated with colons. On Cisco systems, you will see 4 hex digits followed by a period. Let me show you actual screenshots. On Windows, if I run the ipconfig/all command from my command prompt, I'll see under the item physical address, my MAC address represented with dashes separating the different bytes. In Cisco, here's a switch, and I issued some command. It doesn't matter what the command is at this stage, but notice that MAC addresses are represented 4 digits followed by a period. And here on my Mac, and the same idea on Unix systems, notice that it's the different bytes are separated by colons. Okay. So when we talk about MAC addresses, it is important to be aware there are 3 classes, or 3 types, I should say, of MAC addresses. There are unicast, meaning you mean to talk to one single destination. Broadcast, you intend to talk to everyone. Or multicast, you intend to talk to a group. Now, the one thing that you want to keep in mind is that the source address, the source MAC address, will always be unicast. Why? Because it's coming from one single node. These 3 possibilities occur with the destination. The recipient can be one or a group, but the sender will always be one. So let's look at one scenario where this computer is trying to talk to this web server, and they're both on the same LAN. As you can see, they are connected through a switch. So this computer, when it packages a frame, notice it places its own MAC address, okay, in the source field, and it places the MAC address of the receiving computer in the destination field. So this is an example of unicast, very straightforward. The other case would be, what if this computer would like to send an announcement of some type to all the computers on this Ethernet network? Notice here that even though in general LAN is a shared medium, everyone receives everything, but they drop if it's not intended to them. In this example, we're talking about the communication is intended to everyone. So in this case, to reflect that it would like everyone to receive it, what the node does is it places this special type of address, which in binary is all ones. Okay? So all 48 bits are ones, which when you translate to hexadecimal is going to be all ifs. So when a node receives a packet with the destination being all ones, it says, okay, this is a broadcast, which means it's also meant for me. And this applies to this and to this and to every node on our network. So this is the second type of Ethernet addresses. The third type is multicast, where a node is trying to talk to a group. Now, you might be wondering where would this basically be needed. Let's say we're having a virtual classroom where I'm logged in and you guys are also logged in, and we're all within the same network. We don't have to be physically there, but we're all connected to the same network. In this case, basically one node is trying to communicate with a group, not with everyone. So how does it do this? Well, what happens is, to indicate a multicast destination address, it begins with these 3 bytes, 01005E. For the remaining 3 bytes, however, it gets these from the destination IP address, which, as we will see later on when we discuss IP, this is a multicast IP address. Okay, so it copies the last 3 bytes from here, the 00200, which when you translate to hexadecimal is going to be represented as 0000. That's for the first 2 bytes, and then the 200 here is basically, if you were to convert it to hexadecimal, is the C8. So again, multicast Ethernet addresses are created by always beginning with this code 01005E, and for the last 3 bytes it copies the last 3 bytes of the destination IP address. So these are the 3 types. Okay, so if you remember with the train analogy, we saw that, you know, even though virtually you wanted to go from San Francisco to New York, practically and physically that's not how the communication occurs. Likewise, we said communication involves 2 types of addresses. IP addresses, which reflect logically where things are heading from and to, so the original source and the ultimate destination. But then physically the communication may involve multiple hubs. Okay, so you need both. Now, to understand how this works, a very interesting analogy is basically to find a computer, just think that a person bears a name, has a name, and that name doesn't change. Okay, so it doesn't matter where they live, the name is always the same. But then a person also has an address. The address is based on where they live, which means it can over time change. How does this apply in our case? Well, think of MAC addresses as being the name, which doesn't change. Meaning, let's say I have this computer here, okay, which has a MAC card inside it, and that MAC card has an address. If I take this computer, unplug it from this network, it's LAN A, right? If I unplug this computer and move it to this other LAN on the other side of the world maybe, and I plug it in, that computer is going to have the exact same MAC address. Why? Because again, we said the MAC address is burnt on the card. It doesn't change. This is like the name. It never changes. However, when it comes to the IP address, it's a very different story. The IP address is meant to propagate you from the original source to the ultimate destination. So what happens is, let's say this computer happens to have the IP address, let's say 250.10.1.0. Okay? If you remember, we said IP addresses have 2 sections in them. A network prefix to reflect which network the computer is on, and they also have a host ID. Okay, so this computer, let's pretend 250.10.1 reflects this network, LAN A, and the 0 refers to this 0. Well, let's change this to a 1. Okay, and the 1 refers to this computer. Okay. If I move this computer now from this network to this other network, can the IP address stay the same? And the answer is no. Why? Because remember, the first portion needs to reflect the network. If I moved it to another network that has, let's say, the address 100.10.5, then obviously the IP address will need to change to reflect a prefix that matches where it is located, just like a person's address. So as you can see, MAC addresses don't change regardless where you place them. IP addresses need to change because these are used to help in routing and forwarding traffic to a destination. So they have to specify the network where something is located. Why are things done this way? Because it makes locating things faster. So for example, just like mail analogy, let's say someone sends a mail from here within the US to someone in Canada. All the mail people will care about is this needs to be forwarded to Canada. They don't look any closer at it. But once it makes it to Canada, these guys, maybe a main hub that's located here will say, okay, to which province is it going? And let's say it needs to go to Nova Scotia. So they forward all the traffic that's meant for this province there. Once it makes it there, now these guys know the local towns and so on. So once you go close enough, then and only then you look at the actual physical address within, like the street number and so on. So again, why do we need IP addresses to reflect which network? To make forwarding much faster. Then why do we need the physical addresses? Because it makes locating moving things one hop at a time. Okay, so let me show you an illustration of that. Let's say here is a switch. So again, a whole bunch of ports, and here's computer A, B, N. Okay, so computer A, computer B, and computer N. So this is a LAN. So this is LAN. This is a very important example. LAN 1. Okay, let me repeat the same thing here. So here's LAN 2. Meaning LAN 2, what does it have? It has a switch. The switch has ports. Okay, and different computers are connected to the different ports. But then what's outside a LAN? Well, eventually you have a router. Okay, your default gateway. And then maybe the router is connected to a second router, and then maybe the second router is connected to a third one, which is basically acting as the default gateway to this one. Now, how does the communication occur? If you remember, now this is one LAN, right? LAN 1. And this is one LAN. The question is, this router here, does it belong to the LAN, or is it outside the LAN, or where is it located? The answer is, yeah, one of these ports on the switch is going to be connected to the router. That port on the switch is part of LAN 2. Likewise, this port on this switch is part of LAN 1. Okay, so that's the boundary of LAN 1. So the router is partly in this LAN. I say partly because you see this other portion here belongs to this other network. So this is an independent network. This is an independent network. So now let's say you're communicating using IP, saying, okay, I'm the sender. I'm trying to talk to computer here. So I specify the IP address. How does the physical communication occur? Well, first of all, since this computer that's sending and the router, the default gateway, are on the same network, these two can talk using MAC addresses. Okay, so it looks up this router's MAC address and sends it to it. Now this router R1, what is it going to do? It will basically look up the IP information, say, okay, you need to head toward this guy. But how does it send it? It packages it in an Ethernet frame, because guess what? This portion of router 2 and this portion of router 1 are part of one network. Likewise, this portion of router 2 and this portion of router 3 are part of one network. So each time communication is happening over MAC, over one physical network. Does that make sense? So I don't expect an answer. Let me repeat drawing this. So here's LAN 1, LAN, because that got cluttered. Here's LAN 1. Here is LAN 2. And here, let's just keep it simple. Here's one router, and here's the second router. Only two routers in between. Let's call this one R1. Let's call this one R2. Okay, so again, this interface of R1 belongs to LAN 1, while the second interface doesn't. This second interface is part of this intermediate network, which also this interface of router 2 is part of. So in this example, we have one network, which is this one, LAN 1, okay? And this is the second network between router 1 and router 2. And then here is the third network, which is this interface of router 2 plus LAN 2. So three networks in between. So when IP communication occurs between a computer here and a computer here, what's going to happen is, first, physically, it packages that IP packet into a frame sent over the same network, network 1. Then the router does its magic to determine how to forward. And now it sends it over its other interface because it has double subscription. It's part of LAN 1 and LAN 2. And now it sends over this one using the destination MAC address of this interface of router 2. So again, communication at the MAC layer is happening using on the same network. Once it makes it here, again it does lookup and it says, okay, I know how to forward this and I'm part of this LAN 3. I hope this made sense. This is extremely important for us to understand why we need the combination of addresses, the IP addresses and the MAC addresses, and how they work in tandem, where basically the IP addresses are used from the sender to the destination, and they're being looked at by intermediate routers for efficient forwarding by looking at the destination network. Okay, and the other piece is for the physical communication occurring, within a network, within a network, within a network, one hop at a time, is happening by repackaging these packets within MAC frames. I seriously hope this made sense because this is extremely important. If you need to, please go back and rewatch this segment. Okay, so obviously in my little drawing, which was very untidy, but it's okay. I hope you get the idea. So notice here this computer in Paris is connected to router. This is its default gateway, as we were saying, right? So this is one LAN. And now this one here over fiber optic to a microwave satellite dish is a second LAN. So here's LAN 1, here's LAN 2, and here's LAN 3, and so on. So every time, even though the communication, the exact same IP source, the exact same IP destination as it propagates, but physical communication is occurring within the same LAN. The nice thing is that these routers act as multiple subscriptions, like you have 2 gym memberships. Okay, so this router, it's part of LAN 1 using this interface, it's part of this LAN using the other interface, and the same process continues for the other one. So physical communication, just like the train analogy, when you hopped on a train, when you got off a train, that was one one leg of the communication, one piece of the communication occurring over a single LAN.